When did nanotechnology start? I need some answer, please. Tomorrow. One. I need one more. Oh, another one. I did not hear you. Oh, it's Roman. I think all wrong. Yeah. It's all wrong. Because actually, nature had made nanotechnology, I don't know, since beginning of time. You go to the beach, silicon oxide nanoparticle. If you're going to measure, there wouldn't be some nanoparticle there. So, but in any way, so what is technology? So when I have to say that, like some of you already see this very famous Lycurgus Cup, and I did see it from the website of the British Museum, but I had to make it myself, the trip there, and for that one photo, it took me 1 hour, because there is so popular that so many people in the British Museum and just get a picture that's nobody in the background. But the reason I took the picture, so you can see that how you normally look in real life, and it's in perspective in relation to my size of the body. So it is a very special cup. It is really special, and I give you the reason why it is special. And it's just not only because it's red in the transmitted light and the green in the reflected light, because some of you already know, but what is really interesting is that there were a scientific study of this cup, and they did the X-ray, and it's glass, and they did found that it contained the gold and silver alloy. And so the color was given because of this alloy in the cup. But that's remarkable because you see that how the glass, they can make it intricate pattern, and also in the body of Lycurgus, it's that more pink than the other. And the reason it's so remarkable because it's not reproducible. And it's not that what you want. Because for us, when we make something in the lab, we have to be reproduce it. So the reason that they are so rare, because hardly you can reproduce it. Because what you need that in order to make this glass beautiful, you need to make sure that the concentration of this alloy, you need to know that what is a particle diameter, and what is the ratio between gold and silver, and what is the oxidation state? Because that's only gold alloy, which it goes 0 and silver 0, but they can also exist in the oxidation form. And then what is the temperature of the heating when they're making this glass? And then the atmosphere when they perform this, and the distribution and the growth of these particles during the glass making. So none of these will really be reproducible. So that's why that so many cups could be made that time, and very rarely that exists. So yes, they are very valuable. You know what I mean? But for our enterprise today, when we make the nanoparticle in the lab, we have to tackle and avoid this problem. So then we talk about, again, some people stating 1856. So because Michael Faraday, he interested in studying of the matter interaction with light. So he wanted to study the thin film. And so in his Beckerian lecture, or later on published in Fin Trans, it is peer-reviewed paper. And you can see that, I hope you can see on the screen with the blue arrow there, it is 1 of 282,000th of an inch, and calculate out that it's 90 nanometers. So it already, you can see that Microfluidic already make like thin film, and now modern day we call it nanotechnology or nanofilm, right? So then he also, he studied, and the color will be changed. So in the picture, you can see that in the basement, that the gold corridor he made during his time, and the box originally on the desk, that's from his time. And so he also he got experiment to look under the microscope, and he saw that the transmitted light is green, and that's from his note. But what you can see now is that you can see live in your eyes of his original microscope slide, where he got the thin film of gold, and you can see this fantastic effect live. So you can see that it transmitted light is green. Yeah, it's clearly green. And now you see that beautiful gold color. So that's what Microfluidic studied, that interaction of matter and light in those days. And we are so privileged that you are in the audience. You see this live with his original sample of over 166 years. Yeah. So we knew that he made the thin film, and from the wash, he collect some red ruby color, and it was written note in his lab book. And later on, they want to publish the notebook, and they want to sell it. So in order to sell it, they call it diary. And but remarkable of the way, a very systematic study of Microfluidic, that he indexed his work in the paragraph. So we can read his note. It was transcript from his hand note, which is here, hand note, into a transcript, and you can study his study. And then, so 11 years ago, I was privileged. I work here at Royal Institution, my lab upstairs on the 3rd floor. So I work in the basement, lining up all of his original gold soul, and I use a laser light to shine through to see that how much I can go far with my light. And the light scattered, and the scattering of light, that is a Tyndall effect. And Tyndall was here. So he was a professor of natural philosophy in 1853 to 1857. He was the superintendent of the house, and he was director of the laboratory, and also honorary professor here as well. So that's for the Tyndall. And then now you could also see that the Tyndall effect on the original gold soul made by Microfluidic, which is 166 years old. So that is a scattering light, and that is a Tyndall effect. And Tyndall effect on gold corridor, and you see it live in the audience. So that's great. Thank you very much. So you see that there are now 3 bottles, and I said to my colleague that Oh, this was from Microfluidic. I said, oh, it's maybe fake. Somebody put gold salt in there. And the historians say that no, they are Victorian bottle. So this authentic, they was in his time. And this bottle, it looked very clear because some of the particle precipitated down. So you can see light scattering, and you can see the pink and also the red color is still scattered very well there. So the first paper he published, and I think for me it was almost like the first paper in nanotechnology, and he mentioned really well at the bottom two lines, he said that if the solution was weak and phosphorus clean, and the gold reduced is exceedingly fine particle. And it's the way how he described it, really poetic. And then he said that which become diffused and produce a beautiful ruby fluid. So that's so beautiful that he described the scientific experiment and the color. But here, that giving it clear that, for me, that nanoparticle started at his time. And I just giving you some couple of excerpts from his paper that he deliberately make the gold salt not that only from the accident from the wash, because he called it fluid preparation. And then he also listed the different kind of chemical he using that. So he used phosphorus, he used carbon disulfide, he used gallic acid, tartaric acid, so on and so forth. So here is a picture of this very page you see in front, and you can see that they a little bit bigger than our A4 notebook here, but you can see that he beautiful handwritten note of his experiment, and it was transcribed into a book, and later on you will see on the way out, and then we can read that transcript and follow. And then on the first paragraph, if you can see it very well, it said gallic acid. So he used gallic acid at one of his reductant to make the gold nanoparticle. So make the record really straight that he did make the gold solution, the salt, not solution, the salt. So how we make the gold nanoparticle ourselves? So now in the modern day, we use citrate, so that means lemon juice, and gold salt. We make that. So the reduction, and we form the nanoparticle, and you can see the image of transmission electron microscope, and you can see that evolution over time, that the color getting darker and darker, and then it turned in also his described color, beautiful ruby fluid. So then later on, we can make the nanoparticle of the different sizes, and why they have a color, then like why do they have a red and all of this orange color? He already described that because it's reflected, it deflected, it transmitted, it refracted, and it absorbed. All of this phenomenon of light interact with the matter, which is a gold nanoparticle in the solution, giving you that optical effect. So you can see that the absorption spectra, and with the bigger particle, it moves the peak into the longer wavelength. And one thing that nowadays we have to take care of this gold or any type of nanoparticle is the stabilization. So there are different kinds of stabilization. So you look into the physical stabilization, that they're dispersed well in the solution. You look at the chemical stabilization, but here I'm looking at kind of stabilization in a solution. So there are two mechanisms to keep them stable and not aggregated and falling down at the bottom of the bottle, like this bottle, and it needs to be suspended in the salt and not a solution, because solution is meaning like they dissolve, but not because you are two-phase. You have a solid phase of nanoparticle, you've got liquid phase, so they call it salt, okay? So you need to have an electrostatic repulsion So they have enough charge that they are separate apart. And then you also, but that's not stable when you're adding acid because you change the charge, or you set like salt electrolyte. So you need to have another stability mechanism. They call it steric stabilization. So either use the big molecule like a protein or polymer. So that's something to keep them apart so they are not getting stable. Apart, so they are stable. So now we exploit the optical property of the nanoparticle when they come together. So when gold nanoparticle very well dispersed, like you can see here, they will have a red color because you can see the peak at 520. So they absorb light of that 520. So that very light missing because get absorbed, that giving you the red color. So when you're going to have some control aggregation, bring the particle together, so electromagnetic wave interact with the nanoparticle when they are clumping together, will be different when they're dispersed. Then they absorb light at a longer wavelength, and you can see that the B, they absorb at a long wavelength. And now the absorption at a different position, and that's going to give you the color. It turned now from red to blue, okay? So how are we going to exploit this phenomenon? So citation is only one the metric, not that important. The only I'm giving that number there to say that versatility of this assay, that when you can have some kind of aggregation and you can do some kind of detection. So here is an immunoassay. Now, we unfortunately go through the pandemic with the COVID, and we all know about immunoassay, antigen COVID test. So antibody is a letter Y with 2 binding sites. You got the gold nanoparticle with the protein A, and this antibody specifically binds to the protein A. So you're going to have this grabbing of antibody to the nanoparticles. But you have to see that it is a overall effect. So that immunoassay is antibody antigen, and antigen can be a protein, can be spike protein on the COVID. And then so here what you do is that you got this gold nanoparticle surrounding with the protein A and the antibody specific to protein A. You adding them, they aggregate because each of the antibody will bind to one gold nanoparticle. That gold nanoparticle can bind to another antibody, and another antibody bind to another gold, and they bring the network of the gold nanoparticle, and it change color to blue. So this is a very, very lucrative business, pregnancy test, using the gold nanoparticle assays. And also in 2020, when I did writing the review of the different detection for COVID test, and I did cited a paper, people mentioned that they used this gold color chain assay for the COVID test. And so here you can see that when they aggregate, the nanoparticle all clumping together, and it's overnight, it forms these beautiful particles, flowers that I call it a red daisy. So this image that contains about few 10 of the gold nanoparticle. So as I mentioned at the beginning, why the Lycurgus Cup is really rare, because you can never reproduce it. But for us, we go into the extreme to look into how we control the reaction. So here I just give you a very quick glimpse that we look at the way how we're stirring. So when you do the synthesis reaction, you can stir, and you're not aware that by stirring slow or fast, you may change the mass transfer. That means how the material come together to form nanoparticle, and the particle could be polydispersed or monodispersed. Okay? So then move on from that, we also make like now gold nanorods. So we could make them very homogeneous in shape, and we tune the aspect ratio. That means the length of the rod to the width of the rod, and we had to fine-tune them. And you can see that the spectrum there, because now with the rod, you have light going vertically and horizontally. So then you have a dampened peak, that what you saw before of 520, and you have an increased peak at a longer wavelength. So people have been using this absorption of gold nanoparticle for different kind of application, and I'm just giving you some example of how we propose this gold nanorod can be used for different kind of application. So when we make this gold nanorod, we made them in C-type. It's a molecule that positively charged, and then we're going to add DNA with the phosphate backbone. It's negatively charged. And remember that the steric stabilization and electrostatic stabilization. So now you're going to neutralize the charge. So they are no longer repulsive, so they aggregate together. And because they aggregate together, and you can see that on the spectrum on the top right, you see that the change in the longer wavelength. So by seeing that change in the longer wavelength, you can do the detection. Now, if you continue to add more of the DNA in, and then you pass the neutral point, and then the system becomes negative and becomes stable again, because then you're going to lose your signal. So that's why we call it inverse sensing. So you can also use this as also like for assay of the extracellular DNA using this the same technique. Okay, so now I move on to the problem of infection. So before the COVID, infection already a big problem, because you will have a resistant bacteria. It's costing a lot of money. And also in the hospital, some people go to the hospital. They are not dying of their disease, but they're dying because of they're co-infected with some kind of infection in the hospital. And so this is a big problem. And how are you going to solve about it? So you have to clean it, so you can have a routine cleaning, and it's not only practical, or you can have some very deep cleaning, but then it's only like 40% in the contact with the patient, so you cannot really do that. And so you have a different way of thinking, like you have a little robot coming to hospital with a UV light, but then the most contaminated plate is just like in the keyboard with the nurse was register, or where the patient are calling for the nurse, and that cannot be done. So what we propose is that we could look into these gold nano rods and gold nano star. So you can see that the red spectrum, it is from gold nanorod. You can see that typical peak there, and then also gold nanostar. And the color of the gold nanorod is on this size that you see that I put next to the TM. So we also look into the transmission electron microscope to see how they look like, and also my colleague in Singapore look into that the electrical field mapping, so you can see that how this plasmonic play within the different structure. So then what is the practical of that? So you have the dye, they call it like CV, crystal violet, and then you put together with the gold nanorod, and you embed it into the polymer film. But it's really important that you have to choose the gold nanorod at the right aspect ratio. So we choose something short and fat. So we make the absorption peak move into the lower wavelength, so that it coincides or overlap with the crystal violet, so then you can have a plasmonic coupling. And because if you have this plasmonic coupling, you could really form ROS, reactive oxygen species, and you can kill the bacteria. So the data we're showing here is that we're testing this film on E. coli, and for 4 hours, you can kill 5 log. Log, that means every log is like 10, so you can kill the bacteria. So that's one of the applications. So that's some of the application of the plasmonic nanoparticle, and you understand what is a plasmonic. So it's plasmonic because surrounding the nanoparticle, you got this plasma of electron, and when they interact with the light, you can exploit them for the different application. So now I'm moving to the next part, is that the magnetic nanoparticle or magnetic part. So I understand that this picture was originally, the lab, the original lab, you can see it now in the basement, and you can see that the original electromagnet and Microfluidic using that. But there is a series of different magnetic devices he made. So the one in the middle is a ring coil apparatus. So he used the steel, and then the wire from the bonnet, and then the everyday cloth that he wrapping up and making that ring coil apparatus. And then the one you see now in the museum, it is a magnetic optical device, for he studied that magnetic optical device in the museum. So I would like for you to take away something why we study magnetic nanoparticle and how is this important. It's interact with the field. And by the way, you only have a pleasure to look at it maybe for 1 minute, but it's taking us a few months to making this demo for you. But its pleasure is ourselves. We had, we're laughing our head off in the lab. So now I want you to see that the one on the left and the one on the right, they are at a different magnetic field. So one thing I remember for you to take away today is that field is important. The magnitude of the field is important because the magnitude of the field will interact with the matter differently. So if we have a higher field, in this case, you can see that the spike showing you differently, and with the lower field. So that's something I want you to take away. And now, let Mai enjoy his toys. It's amazing. Thank you very much. So what is real-life application when you have a magnet interact with a magnetic nanoparticle? So I just give you one simple example. So we can make this gold nanoparticle, magnetic nanoparticle, and this magnetic nanoparticle can interact with the bacteria. So what you can do is that you use a magnet and you can pull it down, so you can concentrate the pathogen, and you can also to separate it, and then helping the detection. So even with the COVID test, people already thinking of how they can make the detection better and with higher concentration by using this magnetic separation. So that is very simple. So magnetic separation is a big field. So I just give you only a quick example. So I originally worked with gold nanoparticles, and I tumbled in magnetic nanoparticle, and it was so fascinating because there were so many things you could do with a magnetic nanoparticle. It depends on the chemical composition, it depends on the different size, it depends on the different shape, it depends on the magnetic field, and then also it depends on the temperature. And and it is fascinating. There is so many variables you can work with it. So first, I edited my first book. It's very practical because I want that every student come to my lab, read the book, then that's my job done of the introduction to the field, right? So then that's it. And then the field of booming. There was so many different activity with the magnetic nanoparticle, and people say that, why are you editing books so often? But I really want to capture the activity in the field, so that's why there was a second book. So again, you're asking then, okay, so what are the applications? So I'm gladly to say that it is one of really important is that magnetic particle using as the chaser for cancer staging. And Professor Quentin Pankert, he's right in the front row, and Simon here as well, the inventor of this technology. And I was told that 32 million is the revenue from the company, and 250,000 women has been treated with this technology. So basically that he got the magnetic nanoparticle inject into the lymph node, and he so cleverly designed that it giving some audio sound, and then so surgeon can really identify where the cancer are, and then you don't have to use the radioisotope. Okay, so this is fantastic, and this is a work. It was done before, but a lot of that was done here as Royal Institution in the third floor, our lab, Professor Quentin Pankert lab, and my lab on the third floor. So if you want, you can come and visit, and also the exhibition lab at the basement. You can see that where we have all the characterization technique there. So then I'm very passionate about another application, is that magnetic nanoparticle for cancer treatment, and how you going to have a cancer treatment with a magnetic nanoparticle. So there are treatments for cancer right now, but each of them will have some limitation. So we propose the new modality of the cancer treatment is a magnetic hyperthermia. So you got the magnetic nanoparticle, and if you can inject directly into the tumor, and you use an alternating magnetic field, and the spin within the nanoparticle will follow the field, and the particle also possibly tumble up and down, and you will have a two effect. Not too scientific, but you have a Brownian, because you know the Brownian experiment in high school, that the particle are tumbling up and down, and the neo relaxation, and then two of that effect heating up the nanoparticles. So when you're heating up the nanoparticle, you're going to kill the cancer cell locally, so you avoid this side effect. And this is really, really exciting. So, but why people know about this technology and why it's not still available? Because there is some challenges that the particle you need to use, that you need to have a very high dose. And you need to produce a lot of them, because 1 in 2 will have a cancer in their lifetime, and not all cancer will be treated with this modality, but some of them, even that, you need a large amount of number. So when you had to got a production, that you make sure that you can produce them with the large quantity, okay? So then, now, we need to have a particle that's good, that they call it like saturation magnetization. What does it mean? So that means when the particle here, like the ferrofluid, you introduce a field, they become magnetized, and so that with the increase of field, the magnetization going up and up and up, and at some point it becomes plateau. And that point, they call it saturation magnetization. And with this saturation magnetization of the different materials, you can compare that, student A can make better than the student B, or lab A can make better than lab B, because this saturation magnetization, you can standardize them and making them. So this is my classical table. This is almost like the compass since I started to work with the magnetic nanoparticles. You want, number one, I want iron. Yes, good. Iron cobalt, yes, we go for that. Cobalt, we also go for that. And I go for each of them with a few examples for you. So iron, very high saturation magnetization, but the standard reduction potential is very negative. What does it mean? That means that your bicycle, you leave it out there in the rain, it will get rusted. But Tutankhamun mask, 5,000 years still there as the Cairo Museum. So that means gold don't get oxidized, but iron get oxidized very easily. So when iron oxidize, it becomes iron oxide. And it's going to change the magnetic property. You can see that the lower value on the table there, they reduce the saturation magnetization significantly. So there is a challenge to make a dream materials of iron 0. We also could make the cobalt, they are a little bit less saturation magnetization and a little bit easier to work because they're less prone to oxidation. We also make the iron cobalt and, still now, we still try to making iron cobalt for the different varied application, and we also try with iron platinum. I will come into the iron oxide later, but here I just give you the example of, I call it this micro iron 0 firework. So here, not even nano. This is a micron size. You pour it out, and it interacts with oxygen in the air, and it bursts into the flame, no longer iron 0 valent. You come back to the iron oxide. So here you saw on the table the iron platinum. I just giving you here that, it's an hour effort to making of the nanoparticle of the different shape, because you have a magnetic anisotropy. Shape will play some role in the magnetic property. But when I started this work, the reason I make the different shape was that when the gold nanoparticle, they use for the immunolabeling inside the cell. And if you want to study the different event, you have 3 different sizes of nanoparticle, because organelles within the cell are very small, so the nanoparticle, you get them quite small. So you cannot see 5 and 6. Because 5 and 6 nanometer, they are the same population, you can't really distinguish them. So the best you could have like 5 nanometer or 10 nanometer or 20 nanometers. So then my idea that, okay, if we can make up the different shape, then you can see them very clearly under the microscope. So that was originally why I inserted into those shapes early on of the work. So whatever we make, we need to characterize them so that we understand why they're forming the way they were formed. So one of the techniques we use is that the high resolution transmission electron microscope. So you can see that different crystal lattice, and by known crystal lattice, you can indexing that are they iron oxide or are they iron platinum, okay? And then routinely, we use many characterization techniques, but one of them is that we need to analyze the structure by X-ray diffraction. And here, it's really unique example of RI heritage. You have the so far father and son both got the Nobel Prize, and so Sir William Henry Bragg, he was also director of the Davy Faraday Research Laboratory here, and later on his son were also the director of DFRL here. So they are really, really the key person of the Royal Institution in those days. And their prize was for their work on the X-ray diffraction for analysis of crystal structure. So then, again, I am probably the most privileged person that I was allowed to get into the archive, and luckily I can got a picture of his original note, write it down, of this very famous or very routinely used Bragg equation. So when you got the X-ray coming in with a different crystal plane, they will reflected there, and then by working out, and then you have an X-ray coming in, and then you got the rotation of the plates, and then with a different angle. So by using that, you can characterize the particle. So this is a very routinely standard X-ray diffraction pattern that we obtain with all of our nanoparticles. But this cannot be done without the work of the Braggs. So we are really standing in two giant, I mean, how many soldiers of, like giant soldier from the Braggs. So yes, so that's a really rich heritage from the Royal Institution. So I have to give you this picture because I love it, because you can see that it's so monodispersed. What does it mean? They got very regular in size. And you can see that the hydration TM, they are very crystallized. And this is a picture that drawn you to here today. It is called one Faraday nanoparticle. So it is very, very interesting story of this work, that if you remember that on here, the list, I'm saying all of the things that the Lycurgus cups could not be reproduced, and we try to understand those things, right? So you can see that you have a reaction, you have a cobalt salt, you have an iron source, and you have some ligand. So ligand helping to make the particle in the way they different size and the different shape. So they are oleic acid and olein-lamine. So you can have a different solvent. And then going down, you can have a series of the different solvent. And then what is the ratio between them? And how you're going to change the concentration of the ligand, and how you're going to change the concentration of the solvent. And systematically, you study, you can have a repertoire of the different shape. Now, you have the same starting materials, but you have a different shape. So for us, we need to understand as much as possible our synthesis, so that we see that what is the cause to certain size, certain shape are forming, and only then we can reproduce them, right? So that's not like the Lycurgus cups, because I can send you the beautiful, this advertised purple octapod picture, but I can never reproduce that. It's maybe very valuable, I can be very rich, but then, it's not good anything for any other application. So here I just say that, we try with remember my compass table, that I also make cobalt, iron nanoparticle, but they prone to oxidation, so we're coating them with a layer of platinum, and we use a polymer to make them disperse in the water for different application. So here that how we make the one that I'm dreaming of, that is the pure iron nanoparticle. You know that it's not possible. So here we control the synthesis so that we make the iron oxide layer in a controlled manner. Because what we observe that it doesn't matter what size of iron nanoparticle, the techniques are the same. So we increase the core, and then we could have a higher magnetic moment of the iron oxide, iron oxide core shell structure. And you can see that the white one there, it does like how it looks on the TM, you already see it, the core shell structure. But then you look in the scanning transmission electron microscope or elemental mapping, you can see that the red is signified for oxygen, and the blue is signified for the iron. and you overlay them, and you can see that clearly that inside you have more iron. So you have this core shell structure. So we also characterize them for this saturation magnetization that I mentioned before. You can see the curve there, it's going up and it's saturated. And so we characterize the magnetic property as well. And then one other parameter which is derived by Professor Quentin Pankert is this INP. It's like intrinsic load power. Because when you use a higher field and higher frequency, you will have a higher heating. So you obviously want to report that I have a really high heating, but you use very high field and high frequency. So Quentin make people have to be honestly reporting by just standardize that by divide by the h square and then the field, and then you standardize with field and frequency. So what you left is an intrinsic loss power that the data that we can compare between the different systems. So on the top of the table, that was the commercially available iron oxide nanoparticle. The value is about 3.1, and our iron oxide nanoparticle make improvement. We got 3.8, but then our nanoparticle stable for 2 weeks. Remember what I mentioned about the stability. So here now, I'm coming back to this table. I show you different example of my compass table of what the different system I want to have. And then I had to come back to something very modest, iron oxide nanoparticles. Why? Because people are dying of cancer right now. We need to have a treatment. We cannot really wait for something really nice, fancy, shiny, fantastic, but not getting approved to inject into the body. So iron oxide nanoparticle is already approved for the FDA because they used as the T2 contrast agent. So we go to the modest system of the iron oxide nanoparticle, but that is the quickest way we could go through the regulatory approval for the treatment of the cancer. So that's why we stick with the iron oxide nanoparticle. Right, so that was history before that, but I'm just talking about now one of the way of making the iron oxide nanoparticle that we need to make them in water. Because you can make them in high organic solvent, but our body mainly contains water. Blood is a water base. You cannot inject the organic solvent. So unlike gold, in 1856, Faraday made gold nanoparticle in solution. It's only 1981 where René Massat published the paper that he using two salts, ferric iron and ferrous iron, and with ammonia, and he formed the co-precipitation method that forming the nanoparticle. And they did do the characterization by the XRD, and they also found the size with 12 nanometers. So then this is a work we published in 2012, but actually this work started at the Royal Society Science Summer Exhibition, and in collaboration with the RI, Professor Quentin Pankert, and our group have a big exhibition, and we want to show the public how we make this iron oxide and sodium hydroxide. It's very caustic. So we want to something milder, so use baking soda. So we could make the nanoparticle using baking soda. Then Christina was pretty student between myself and Professor Quentin Pankert, and we systematically study. And from that work, what we show that with the mild base, you form a lot of intermediate. And remember that iron oxide got like more than 10 phases, and not all of them are magnetic. So then, recently in 2019, we making the nanoparticle using microfluidic system that allow us to control the reaction. And again, it's all about control. You have to control your reaction. So if you look in the diagram, you got a pump, so you can follow the rate. You can also follow the amount injected in, and also like you can raise the temperature really quickly for the reaction. So in this reaction, very much the same with René Massas in 1981 reaction, but what we did was that we could use the synchrotron X-ray to look at the reaction. Again, what we are saying that when we make the nanoparticle, we need to characterize them. And here, it is a landmark paper. Why? Because for now, more than 40 years, and in the field, you can see that people reporting different value of saturation, magnetization, there is no consistency, because they form the intermediate. So when you have two flow and you got the reaction, and you can see that from precipitation, you got orange, the ferrihydride, you got this green plate, it is a carbonate. But then they go into the next phase that where is some ion from this green plate leaching out, interact with the orange ferrihydride, and then that some more ion from the green plate reacting with the ferrihydride forming you this magnetite. That's what we want, that high magnetic moment phase. So we look into the reaction closely from 30 seconds to 10 minutes, and you can see the TM along, and then you can see the size of the nanoparticle and the size distribution. And the D panel, there you see the electron diffraction pattern, and you can see the line coming down. They are the position of the magnetite peaks. And you now can start to see that from 2 minutes, you can see that show the forming there. So the magnetite, and also even here, that 30 seconds, you start seeing the signature of magnetite forming. So it's really important to control the reaction very much early on. So remember this for me, because I will giving you a very important innovation with our nanoparticle based on this very important basic study. So again, what I'm saying that I would like to treat cancer patient, but you cannot avoid not doing the fundamental research to understand. So remember this one, and I will bring back to the story that where we control our reaction in very short time. So then when you talk about nanoparticle, you have to think nanoparticle as a system. Right? So we talk about gold soul of Microfluidic. The question was why his soul were lasting for 166 years or even more, and why some people nanoparticle are crashing out. There are something in there, I would call it ligand, that some of that ligand would protecting his particle to make it stabilization. And it possibly is my suggestion that he might use the phosphorus and also carbon disulfide. They are very toxic, so no bacteria could grow and destroy the system, and also the vial was very close, so nothing really coming in. So when you think about the nanoparticle, you need at the system, because you got the core. The core can be magnetic, plasmonic, can be different chemical composition, but you need the shell. The shell here is really, really important. Why? Because when you inject this nanoparticle inside the body, your body not seeing the core, they're seeing the shell. So the shell here is really important, that how they going to behave. And if you want to have some interaction, you will have a specific. So I'm just give you a very little thing here, like we're talking about the immunoassay, antibody, and antigen. So you need to have a particle, have this antibody, and it's going to interact with the antigen. So you have this specific entity that doing the job of the interaction, okay? So then when you understand that nanoparticle as a system, you can exploit it. So in this work, we use a thermoresponsive polymer for our nanoparticle synthesis. So why did I do this one? It's just purely curiosity. Because my colleague, Cameron Alexandra from Nottingham, come to visit, give a talk about thermoresponsive nanoparticle. Nothing but nanoparticles. And I just came to him, I'm very curious, can you give me some polymer? I can see if I can make the nanoparticle out of it. And we did. And it was a great excitement that I did not know before that we could make the nanoparticle with thermoresponsive polymer. And it turned out really interesting because this thermoresponsive polymer, it dissolves in a hot organic solvent. It allows you to do reaction because at the higher temperature, the nanoparticle more crystalline, the crystal structure is more ordered, it becomes more magnetic. And you can leave it cooling down, and it change phase because it responds to the temperature, and they change the conformation of the polymer, and then you can remove all the hot organic solvent, and you can disperse them into the water, right? So what next? So carry on with this work. We conjugate doxorubicin, is the anti-cancer drug for breast cancer. And we conjugate that with the polymer. And why? Because when you use an alternating magnetic field, you heat up nanoparticle, you also heat up the polymer. The polymer responsive to the temperature, they will release the drug. But more than that, we covalently binding this polymer into with the drug, and they respond to the acid. So the cancer cells are more acidic. So when it gets to the cancer cell, they will break the bond and the drug got released. But when the nanoparticle, if they accidentally get into the non-cancerous cell, they are not acidic, so they not release the drug, so it's not toxic. So it's really important that you got the dual modality of the drug release. And though you can see the bottom line, that where the pH is 7.4 and 25 degree, that low temperature, high pH, and the top line, that where you have a high temperature and lower pH, you have a higher drug release there. So we look into this synergetic effect of the chemotherapy and magnetic hyperthermia. And the data showing that with the two different types of cells, and then we incubate that at the different time, like we monitor after 24 hours and 48 hours. And you can see that the bar, that's only need to look at one of them. That one is that's in the beginning of the control, and this one is that magnetic nanoparticle and the magnetic nanoparticle with the drug. And you can see that the bar are going lower down. That is the cell viability. So you have a synergetic effect that means that the sum is larger than it passed, that you could have a better effect, so you can use lower dose of chemotherapy and helping with the side effect, and also lower dose of magnetic nanoparticle for the treatment. So this work also was done in collaboration with Professor Quentin Pankhurst, and they're very cleverly designed, and I think I haven't seen it anywhere else, and it's still homemade, and luckily, they made another one for us now. This is a pancake coil. So this pancake coil is just on the top of the microscope slide that you can have a very even feel, and you can study that when you got the nanoparticle incubate inside the cell, and you can change the alternating magnetic field and see the study of magnetic hyperthermia. And so this magnetic hyperthermia allowing to monitor the reaction in real life. And from this work, we can see that it's an early apoptosis of nanoparticle, it labeling with a different color of the cell, so that none of the cell would die in 1 hour, and they continue, and then 18 hours they was dying. So it's really important for us to understand that the mechanism of how these cells are dying under the magnetic hyperthermia.
That's the gong.
Fine.
So, no. So it's good. We have one more demo, right?
Yes.
You want to jump? Is there an elegant way to jump to the final demo? Because the guys are really excited about bringing it on.
Yes. So there was the way to jump.
Great. Let's jump, because the guys have worked really hard. So you give them the cue, and we do the final demo, and then we'll do the Q&A.
So I would like to thank my funder, my people at the periodic table, and people at the break table. And it's about a very famous mirror and the picture of our hero, Michael Faraday. And I would like to thank the RI team for all the demo.
So what's this demo, Tan?
That is demo, this the interaction of the magnetic nanoparticle. That's a thank to the RI. How long did it take you to do this one? A few months, right? Is it?
A little.
Just a little. Perfect.